And morning everyone. My name is Wenxin from Tianjin University. So for this work, for scaling with imprecise knowledge, it is a joint work with Heng, Yuan Liu, Professor Keqiu, Zhao, Zewei, Guan, and Zhang from Tianjin University, and Professor Chen from HKUST, Professor Heng from Dalian University of Technology, and Professor Guyue from New York University, Shanghai. So as we know, the flow scaling it is an effective scheme for data center transport design, and its goal is to minimize the flow completion time so as to deliver low latency for data center applications like web search or Keqiu store, something like this. So to minimize the FCT, and many flow scaling solutions try to prioritize the package of small flows over large ones in the switch buffer. So maybe you can see the key lies in the flow size of the information, and there are two lines of prior work. The first line of work focuses on the client 1 flow scaling, and it assumes the precise flow size information and uses it to approximate the SRPT policy. So this approach may achieve good performance, but it is very challenging to be deployed because it requires too many priorities or need to refactor the entire TCP/IP network stack like the HOMA or PIAS. So another work focuses on non-client flow scaling, and it doesn't rely on the precise flow size information and simply estimates the flow size based on the byte sent. So this approach may be easy to implement, but it cannot separate the small flows from large ones from the beginning of the transmission. So it has a limited ability in minimize the FCT. So in our work, we look for a middle point design space dataset. Rather than relying on the precise flow information or no prior information at all, we ask, is it possible to use the imprecise flow size information to minimize the FCT with comedy switch? So let's first see what the imprecise flow information mean. In recent years, many researchers have shown the possibility to learn the flow size information from the past trace using some machine learning techniques. So, but the estimated flow size of the machine learning models are often imprecise. So this means that there is always a gap between the actual and the estimated flow size. So we use a popular machine learning technique called the random forest over 3 public workloads, the K-means, PageRank, and SGD. And we found that at least 34% of the flows have a gap of over 100 kilobytes to their estimated size. So anyway, since we have the flow size information, even though it is imprecise, the next step is how to use it. So the only work we know is that the flux, it directly takes the imprecise information as the scaling input for the schedulers like pFabric. But as our preliminary experiments shown that the average FCT of the small flows achieved by the pFabric with such imprecise flow information can be slowed down by up to 23 times. However, the good news is that we surprisingly find the lower bound part of the imprecise flow information is highly accurate. So our finding is initially inspired from the application's property. From the applications we found many data center network applications and their network flows have the low bounds. So for example, in distributed machine learning, each network flow needs to transfer 1 parameter, which could be 40 bytes, considering various packet headers. So another example is like in large-scale web search, where each network flow needs to transfer 1 page index, which could be typically larger than 1.6 kilobytes. But the application level slow bound may be far away from the actual flow size. So to provide a tight low bound, we again use the random forest technique. Specifically, we keep the full conditional distribution of each random forest tree's decision And we use a quantile regression forest method to build a prediction interval for each flow size. So in this case, we can get the lower and upper bound of each flow. And we again use the 3 workloads, and we find that over 99.9% of the flows can be accurately bounded. So we further give an intuitive visual feeling for these intervals. From this figure, we can find that for the small flows denoted as the red rectangular points, their actual size are mostly close to their lower bounds. So this phenomenon is reasonable because many data center applications usually shows a long tail distribution where most of the flows are short. So this will make the random forest trees to have too many small values in his leaf nodes, and this will make the random forest to give the lower bounds close to the small flow size. So actually, you may have more findings from this figure, like the medium and the larger flows low bounds are relatively larger than the small flows. So please see our paper for more observations. And building on these findings, we designed QCLIMB. So QCLIMB's first component is the low bound-based scattering. And this scattering is based on the low bounds, and it has 2 main phases, the QCLIMB up phase and the QCLIMB down phase. So initially, each flow is mapped to a product based on its low bounds. And during the QCLIMB up phase, the flow will be promoted to higher product queues based on its remaining data size to its lower bound. So if the flow is not yet complete, and after the first phase, it will further go through an additional QCLIMB down phase. So in this phase, it will be gradually demoted to the lower product queues based on its byte descent. So since our previous slides has showed that the medium and the larger flows low bounds are relatively larger than those of the small flows, so this scattering can prioritize the small flows from the large ones from the beginning of the transmission rather than in the later stage of the transmission. So now I will use a simple example to show this scattering design. And in this example, there are 3 servers connected to 1 switch. The left 2 are the senders and the right 1 are the receiver. There are 4 product queues and some flows. The flow 1 has 7 packets and its low bound is assumed to be 4. And the flow 2 has 3 packets and its low bound is also 3. So the number before each product queue denotes the queue thresholds. And based on the low bounds, we can see that the 2 flows will initially enter into different product queues. So the flow 1 will enter into product queue 3, while flow 2 enters into product queue 2. So since now the flow 2's priority is higher than the flow 1's, so the first packet of the flow 2 will be first transmitted. And then the flow 2 proceeds to the QCLIMB up phase, and it will be promoted to priority 1 and finish in this priority. But let's look at the flow 1. It is still in the priority queue 3. So after the last packet of the flow 2 finish, the first packet of the flow 1 will be transferred. And then we also let the flow 1 enters into a QCLIMB up phase. So it will be promoted to priority queue 2, where it transmits 2 packets. And further, it will be promoted to priority queue 1, and in this priority, it only transmits 1 packet. So till now, we can find that the flow 1's lower bound part finished, but please note that it is not the end. So this means that the flow's actual size is larger than its lower bound. So in this case, we will change our strategy and let the flow 1 go through an additional QCLIMB down phase. So specifically, we will pull back the flow to its initially entered product queue 3. And in this priority, the flow will transmit 2 packets. So we will further demote the flow 1 to lower product queues gradually based on its byte descent. And in this case, it is demoted to product queue 4, and where it will finish its last packet transmission. So in addition to the scattering design, we must also address the out-of-order issue. So this is because the QCLIMB up phase will allow the later packets of a flow to enter higher product queues than earlier ones. but the default TCP out of handling will consider this event as loss and trigger unnecessary retransmission. So we present a priority-based loss detection mechanism at the receiver, and its key idea is to leverage the fact that the packets carrying the same priority belonging to the same flow should be in order, and a gap within the same priority should be identified as a loss. So with this approach, we can quickly detect and differentiate the real packet loss from the orderings. So for actual packet loss, we simply trigger the retransmission, and for the orderings, we use the fast and the slow path to guarantee the in-order packet delivery to the application. And at the same time, we customize the ACK for the out-of-order packets to bypass the default TCP ACK scheme, so that the redundant retransmission will not be triggered. So we have implemented the QCLIMB prototype. It only requires end host implementation, and at the switch side, only the strict priority queuing is required, which is the built-in function in the existing comedy switch. So we implement the scheduling and the random forest model inference as the Linux kernel models between the NIC driver and the TCP/IP network stack. And for the out-of-order handling, we implemented it as between the TCP and IP layers. Now we come to our testbed experiments. We use 8 servers connected to one barefoot Tofino switch using 25 GB links. So for the benchmark, we again use the k-means, PageRank, and NSDI workloads from the Flux paper. So for each workload, we first train a random forest model for running 3 minutes using 80% of the dataset. And then we use the trained model with the remaining dataset for testing to do our evaluation. We choose 2 comparisons. The first one is the PIAS. We choose PIAS because it has the same practical features as our QCLIMB, but it is falls short in FCT minimization. And another one is the QCLIMB PIAS. So this is a variant of the QCLIMB. It uses the precise flow size information and keeps promoting a flow's priority from lower priorities to higher priorities based on each flow's remaining data size. And this variant uses the same out-of-order handling logic with the original of QCLIMB. So from this figure, we can see that compared to PIAS, our QCLIMB can reduce the average and the tail FCT of small flows by up to 88% and 97% respectively. So compared to QCLIMB PIAS, it also can deliver only a 3 gap for the small average FCT. We further show the performance breakdown. We find that even though our QCLIMB has small processing steps for the flow scheduling, but it can achieve lower FCT. So for the small flows in QCLIMB, the QCLIMB up phase accounts for 99% of the FCT. But let's look at the PIAS. It only contains one phase, that is the QCLIMB down phase. So this means it will keep demoting a flow's priority from higher priorities to lower priorities based on the bytesend. So this will make it achieve poor performance of the FCT. On the other hand, we can find that across all the shown cases, our random forest inference takes only 3 microseconds, which could be negligible as compared to the FCT of the flows. So we also did the simulation in 40 and 100 gigabytes data center. The setup of simulation is very similar to the pFabric paper, and we again use the 3 workloads. So in simulation, QCLIMB can also reduce the average and the tail FCT of the small flows by up to 46% and 62% respectively. We also compare QCLIMB with the pFabric, and in this experiment, we let the pFabric use the precise knowledge. But even in this case, we found that the QCLIMB can deliver an average gap of 9% to pFabric for the overall average performance, and an average gap of 5.7% for the small average FCT. So an interesting observation is that sometimes the QCLIMB can even deliver a slightly lower tail FCT of the small flows than pFabric. So this is because the QCLIMB incurs fewer packet loss than pFabric. We can see from this table, QCLIMB incurs 30% fewer packet loss than the pFabric. And also most of the packet loss of our QCLIMB can be quickly detected by its priority-based loss detection mechanism. But the pFabric can only detect the packet loss with timeout. So in summary, our QCLIMB has two components. First, it employs a low bound-based flow scheduling to ensure the small flows can be prioritized over medium and large ones from the beginning of the transmission. And it also has faster priority-based loss recovery and the packet reordering mechanism to handle out of order issues resulting from the scheduling algorithm. All of these components are very easy to implement and configure in production data centers. So that's all about my presentation. Thank you.